All right. I'd like to do an example now with the torque equals I alpha equation. Let's say that we have 4 kids on a merry-go-round. Each mass of the kid is 50 kilograms, and the mass of the rotating cylinder that they're having a fun ride on, let's say here, is equal to 100 kilograms, and the radius of this rotating, we'll call it a cylinder, is, let's say, 5 meters. And so let's say that we have an adult that is pushing with a constant force that's equal to 100 newtons. In a tangential direction, always, and we'll keep that constant. So that this adult is such a nice guy, he will keep running around and pushing with the same amount of force in order to give the kids a nice smooth ride and a smooth acceleration. So we'll keep this constant, 100 newtons, acting through that radius vector here of 5 meters. We'll keep that perpendicular to the radius vector r, so that our torque is just equal to Rf, and so that'll be equal to 5 meters times 100 newtons, or 500 newton meters. Remember, we're not calling this a joule because the torque itself is not work. It's when the torque acts through an angle, as it turns out, that we do work. But what we're more interested in here is getting an expression for the torque. Now we'll need to calculate I, and then solve for alpha. Right? So let's say that's our goal here. Let's find alpha for this system. Now this system is 4 point masses and a cylinder. Okay, so I total will be equal to 4 times I for each kid plus I for the cylinder. The cylinder is this big rotating turntable that is like the merry-go-round that's on. Now let's assume there's no friction here. And so this will be then 4 times mr squared. We'll assume that each kid is a point mass that is at a distance of 5 meters away from the center. So this is going to be little m r squared plus I cylinder is 1/2 big M r squared. Okay, so we're just trying to find the moment of inertia of 4 point masses plus the moment of inertia of the cylinder. And this is a scalar quantity, so these things are added together. So this would be 4 times m, that's 50 kilograms, times r squared, that's 5 meters squared, plus 1/2 times m, which is 100 kilograms, times 5 meters squared. So this is going to be equal to 200 here times 25. Okay, so 100 times 25 is 2,500. Okay, and so 200 times 25 would be 5,000. Okay, and so that would have units then of kilogram meters squared plus 1/2 m, so that would be equal to 500 times 25. Okay, and so that 500 times 25 would be 50, sorry, times 25. That would be 1250 kilogram meters squared. So this is 50 times 25. So that would be d times 25. 50 times 10 is 500. Yeah, so that looks good. So this would be 7250 kilogram meters squared for I. Okay, we have the torque, 500 Newton meters, and so now all we have to do is plug in to the relationship torque equals I alpha to give us the alpha value, which is going to be our torque. That was the easy part here, divided by the moment of inertia. And so that would be equal to 500 Newton meter divided by 70, this would be 6250, sorry. 6250. That'd be kilogram meters squared. So that gives us 0.08 radians per second squared. All right, so it seemed like our kindly adult was giving the kids a pretty good ride, but 0.08 or 8 times 10 to the minus 2 radians per second squared doesn't look very significant in terms of a wild ride. So let's go ahead and see what the final angular velocity would be after 5 seconds. Let's assume that we start from rest. Okay, so we'll make a table now of knowns and unknowns. Starts from rest, so the initial velocity is 0. Unknown would be omega final. The time is 5 seconds. And the alpha value is something that we wouldn't have known before, but we're able to solve for that now using torque equals I alpha. So without the torque equals I alpha equation, we don't have enough information to obtain our third unknown. But here we've got it, 0.08 radians per second squared. Go back to our kinematics equations. The other unknown is the angle theta. So we can eliminate all equations involving the angle theta, and that leaves us with omega final equals omega initial plus alpha t. And so omega final then would be omega initial 0 plus alpha 0.08 radians per second squared times the time, which is 5 seconds. So that would give us 8 times 5 is 40, so that would be 0.4 radians per second. So is this going to be a fun ride? Well, I don't think so. But let's just take a quick look at how many degrees per second that would be. 0.4 radians per second times 180 degrees for every pi radians. Okay, so it's going to be 0.4 divided by pi times 180. And so that gives us 23 degrees per second. So let's just see, is that going to be a fun ride? Well, 23 degrees per second. So we're going to go, oh, it's not working. Just follow this along. 23 degrees, I would go about like that. Okay, so that's about 23 degrees. This would be at 30 degrees. 23 degrees per second is about that fast. Not that fast, about that fast. Okay, so the kid is starting to say, why are you wasting my time? This is no fun. You weakling, can't you do any better than that? And so the kindly adult says, okay kids, if you want a fun ride, on the count of 3, I want you to all run to the center. 1, 2,